67. That is the first number. 67 kilometers per second per megaparsec. 1 megaparsec is 3.26 million light years. For every 3.26 million light years, you look outward into space. The galaxies you see are moving away from us 67 kilometers per second faster. That is the expansion rate of the universe. That is what our best model of reality predicts, extracted from the oldest light we can measure, cross-checked against the mathematics of the early universe, confirmed by instruments built at a cost of $1 billion, a number so precise, so internally consistent, that the margin of error is less than 1%. We know this number. The universe told us. 73. That is the second number. 73 kilometers per second per megaparsec. Same unit, same universe. A completely different answer, measured not from the ancient light of the early cosmos, but from the present, from the pulsing rhythms of nearby stars, from the calibrated brightness of exploding suns, from a chain of measurements built step by step, outward across hundreds of millions of light years. A number confirmed by independent teams, using independent methods, pointing instruments at the same sky. A number that the James Webb Space Telescope was designed to disprove. A number that Webb confirmed instead. '67 and '73 cannot both be right. The universe can only expand at one rate. Either the map we built from the beginning of time is wrong, or the map we built from the present is wrong. One of them is a picture of a universe that does not exist. We do not know which one. The number 73 did not come from theory. It came from blood. It took decades to build, a chain of measurements, each one calibrated against the last, extending outward from the nearest stars to the edges of the observable universe. Astronomers call it the cosmic distance ladder. Every rung of that ladder represents a different technique for measuring how far away something is. The first rung begins close. Nearby stars have a parallax, a tiny shift in apparent position as Earth moves around the Sun. Measure that shift carefully enough, and you can calculate the distance to a star with pure geometry. No assumptions, just angles and arithmetic. From those parallax distances, astronomers calibrated the behavior of a particular class of variable stars, Cepheid variables. A Cepheid pulsates. It brightens and dims in a regular cycle, like a slow heartbeat. And here is the crucial property. The period of that pulsation is directly tied to the star's true luminosity. A Cepheid that pulses over 30 days is intrinsically more luminous than one that pulses over 10. This relationship, period to luminosity, is a ruler built into the stars themselves. Observe the pulse, calculate the true brightness. Compare that true brightness to how bright the star appears from Earth. Derive the distance. Cepheids can be seen across millions of light years. They exist in nearby galaxies, which means astronomers can place those galaxies at known distances. And in some of those same galaxies, a different phenomenon occurs. Type 1, a supernovae. The explosion of a white dwarf star that has pulled too much mass from a companion. At their peak, these explosions are nearly identical in brightness across the universe. A cosmic standard candle calibrated against the Cepheids in the same host galaxy. From there, you can see Type 1 A supernovae in galaxies hundreds of millions of light years away, where individual Cepheids are invisible. Measure their distance. Measure how fast those galaxies are receding. Divide one by the other. Get the Hubble constant. Adam Rees and his team, working under the project name SH0ES, have spent 2 decades refining every link in this chain. By 2023, their answer had converged at 73. Not approximately 73, reliably consistently 73, with a precision of roughly 1%. The question was always whether something invisible was contaminating the chain, whether the Cepheids, embedded in the crowded, dusty disks of their host galaxies, were being corrupted by the blended light of nearby stars, making them appear brighter, making distances appear shorter, making the expansion rate appear higher. This is called crowding bias, and it was the most plausible escape route from the tension. James Webb Space Telescope closed that exit. Webb observes in the infrared. Infrared light cuts through dust. Its mirror is 6.5 meters across, more than twice the diameter of Hubble. Its angular resolution is sharp enough to separate individual stars and galaxies, where Hubble saw only smeared light. In 2023 and 2024, Reese pointed Webb at the same Cepheids his team had been measuring with Hubble for years. He examined over 1,000 Cepheids across 5 galaxies, extending the calibration chain out to NGC 5468, 130 million light-years away. The comparison was direct: the same stars, the same distances, 2 telescopes. Webb confirmed Hubble's numbers, not approximately, almost exactly. The crowding hypothesis is dead. The bias is not there. The 73 is real. The number 67 came from somewhere older. In 2009, the European Space Agency launched the Planck satellite. Its mission was to map the cosmic microwave background, the faint thermal radiation left over from a moment 380,000 years after the Big Bang, when the universe cooled enough for electrons to bind to nuclei, and the cosmos became transparent to light for the first time. That released photon bath has been traveling ever since, stretched by the expansion of space, cooling from thousands of degrees to a whisper of 2.7 Kelvin. It permeates the entire sky. It is the oldest light we can observe. The Planck map is not uniform. It contains tiny fluctuations, 1 part in 100,000, temperature variations that encode the state of the early universe. The distribution of those fluctuations, their statistical pattern across the sky, is a fingerprint of the initial conditions, the density of ordinary matter, dark matter, the geometry of space, the rate at which things were moving. From that fingerprint, cosmologists can extract the parameters of the universe's birth, and from those parameters, running the equations of the Standard Model forward across nearly 14 billion years, they can predict the expansion rate we should measure today. The answer is 67, with extraordinary precision, with a margin of error of less than 0.5%. The Standard Model is not a naive or brittle framework. It is the product of a century of cross-checking against observation. It correctly predicts the primordial abundances of hydrogen, helium, and lithium. It accounts for the large-scale structure of the cosmic web, the filaments, sheets, and voids across which galaxies are distributed. It explains the detailed statistical pattern of the microwave background fluctuations across hundreds of angular scales. It is not a guess. It is the most rigorously tested framework in the history of cosmology. And it says 67. 2 measurements, 2 methodologies, 2 different windows into the same universe. 1 looking back to the beginning, 1 measuring the present. And they do not agree. The gap between 67 and 73 is not a rounding error. In absolute terms, 6 kilometers per second per megaparsec sounds small. In statistical terms, the discrepancy sits at approximately 5 standard deviations. In physics, 3 standard deviations is considered evidence of something real. 5 is considered a discovery. A 5 sigma discrepancy between 2 independent methods measuring the same quantity is the kind of thing that rewrites textbooks. David Gross, Nobel laureate in particle physics, was asked at a 2019 conference whether this disagreement should be called a problem. He said no. He said it should be called a crisis. The Hubble tension would be disturbing enough on its own, but it is not standing alone. James Webb did not only confirm the distance ladder, it looked deeper into the early universe than any telescope before it, and what it found there does not fit the standard model either. Not in the same way, not in the same place, but the direction is the same. The universe is doing things it is not supposed to be doing. In the first year of Webb operations, the deep field images returned something unexpected. Scattered across the epoch of cosmic dawn, 500 to 700 million years after the Big Bang, were galaxies. Not the faint, diffuse, chaotic protostructures the standard model predicted for that era, massive galaxies. In some cases, systems rivaling the Milky Way in total stellar mass. A galaxy that required 13 billion years to build in our own cosmic neighborhood had apparently assembled itself in under a billion. Analysis of 6 candidates pushed against the absolute mass limit allowed by standard cosmology. To achieve those masses in that time frame, nearly every available atom in the surrounding dark matter halos would have had to convert into stars with nearly 100% efficiency. Under normal conditions, that conversion rate sits around 10%. Gas is lost to heating, to feedback, to the random violence of the early universe. A system running at 100% efficiency does not exist in the standard model. Then came a complication. Some of those apparently massive early galaxies were later identified as little red dots, compact, reddish objects that turned out, in a significant fraction of cases, to host aggressively feeding black holes. The light from those black holes was contaminating the stellar mass estimates. A galaxy with a hungry black hole at its center produces light the way a galaxy with 10 times more stars might. Webb sees brightness. Brightness is usually a proxy for mass. In these cases, it was a proxy for a feeding engine masquerading as a population of stars. Remove the little red dots. The remaining galaxies come closer to fitting the model, but not all the way. Even after the contaminated sample is cleaned, roughly twice as many massive early galaxies remain as the standard model predicts. The model bends. It does not break, but it bends. And there is more. A study published in Nature Astronomy in late 2025 found that many young galaxies observed by Webb appear elongated, stretched into shapes resembling cosmic filaments, long and narrow, rather than compact and spherical. The cold, dark matter model predicts a different distribution of shapes. These elongated forms match predictions from alternative dark matter frameworks. Warm dark matter, wave dark matter, in which the large-scale structure of the universe has a smoother texture, allowing gas and stars to flow along filaments rather than clumping into compact nodes. Cold dark matter is not one ingredient in the standard model. It is the scaffolding. It determines where galaxies form, how they cluster, how the web of structure spans billions of light years. If dark matter particles behave differently than the cold model assumes, the implications propagate through every prediction cosmology makes. You cannot change the scaffolding without changing the building. And then there is the S8 tension, quieter than the Hubble crisis, but watching from the same direction. The standard model predicts a certain level of clumpiness in the distribution of matter across the universe. When astronomers measure that clumpiness directly through weak gravitational lensing surveys, they consistently find slightly less of it than the model predicts, less structure than there should be, a universe slightly smoother than the equations allow. Rees has called the S8 tension the little sibling of the Hubble tension. Same family, same pathology, a universe that is expanding faster than it should and is less structured than it should be. 2 independent symptoms, 1 underlying condition, unknown. Every crack in a framework demands an explanation, and explanations are not hard to find. What is hard to find is one that works. The most popular rescue attempt goes by the name of early dark energy. The hypothesis is this: in the first few 100,000 years after the Big Bang, before the formation of the cosmic microwave background, a transient energy field flooded the universe, briefly accelerating the expansion rate, then vanishing. If that burst of extra expansion happened, it would have altered the conditions of the early universe just enough to shift the Planck prediction upward. The cosmic microwave background would still look right. The abundances of hydrogen and helium would still work. But the calibration of the distance scale would shift, pulling 67 closer to 73. Early dark energy is mathematically coherent. It is not insane. It is one of the few proposals that could close the gap without destroying the things the standard model gets right. But no one has detected it. It leaves no unambiguous signature in any data set. It was invented to solve the Hubble tension. It solves the Hubble tension and nothing else, which in physics is not an endorsement. A theory that exists only to explain the thing that motivated it is not a discovery. It is a placeholder. Other possibilities crowd the edges. Modified gravity, the idea that Einstein's equations break down at cosmological scales, that the behavior of space itself changes across vast distances in ways the current equations do not capture. Extra relativistic particles in the early universe, beyond the 3 known neutrino species, that would alter the acoustic physics of the pre-recombination plasma. Interacting dark energy, a dark sector that does not stay quietly in the background, but actually exchanges something with dark matter over time. None of these proposals are accepted. None have been confirmed. They exist as mathematical architectures with no known physical foundation. We are describing the solution without understanding what the problem is. And here is the deeper discomfort. Even if one of these proposals eventually survives contact with the data, even if early dark energy closes the Hubble tension, it would mean that the standard model was wrong about the early universe in a foundational way. The model was built from the cosmic microwave background upward. If an undetected energy field was present in those first few 100,000 years, then everything we extracted from that background, every parameter, every constraint, every piece of the story of what came after the Big Bang was extracted from a picture we did not fully understand. The implications of that would not be contained to the Hubble constant. There is a fact at the center of this that should not be allowed to become comfortable. The universe is a physical system. It expands at one rate. That rate is not 67 in one part of the sky and 73 in another. It is a single number, a single reality. And we have 2 methods of measuring it that produce 2 different answers, incompatible at 5 standard deviations. One of them is wrong, not approximately wrong, not off by a rounding error in some obscure calibration, wrong in a way that implies genuine failure, either in how we measure the present universe or in how we reconstructed the ancient one. 2 human enterprises, each built on decades of careful work, each internally consistent, each trusted by their practitioners, and they cannot both be describing the same cosmos. We tend to speak of this as a tension, a careful word from a careful discipline. It suggests a rope slightly too taut, a measurement slightly off, a parameter awaiting refinement. That framing may no longer be adequate. A 5 sigma discrepancy, confirmed by Webb, with the most plausible source of systematic error ruled out directly. This is not a tension waiting for a better telescope. It is a contradiction waiting for an explanation. And the explanation, when it arrives, will require revising something fundamental. Either our understanding of the early universe contains an ingredient we have not accounted for, or our chain of measurements from the present is contaminated by something invisible that Webb has not found, but that must exist somewhere. Both possibilities are severe. If the error is in the early universe, then the Standard Model does not fully describe what happened in the first 380,000 years. The picture we call the cosmic microwave background, the most detailed map of the early universe ever made, the foundation of modern cosmology, is a correct image of an incompletely understood reality. We have been reading it without knowing all the words. If the error is in the distance ladder, then Webb has missed something. The sharpest infrared telescope ever built, designed specifically to eliminate the known sources of bias, has returned data that is still contaminated by something it cannot see. Something is hiding at the boundary of our instruments. Either way, there is a wall. Either way, something is on the other side of it that we cannot reach. We do not know which wall it is. Come back to the two numbers, 67, 73. They have been coexisting in the literature for nearly a decade. They have survived every attempt to close the gap. They have survived Reese pointing Webb at the same Cepheids Hubble measured. They have survived Wendy Friedman building an independent ladder from different stars. They have survived the most precise maps of the microwave background ever made. They are still there. Most crises in physics resolve. Dark energy was a crisis once. The flatness of the universe was a crisis. We have a long history of finding doors where we expected walls. But we have never stood here before. Not with two measurements this precise, this independently confirmed, pointing at the same quantity and giving results this incompatible. We built our picture of the universe from two directions. From the beginning, using the oldest light. From the present, using the nearest stars. Those two pictures should have been the same picture. They are not. One of them describes a universe that does not exist. We live inside one of those pictures. We have built our entire understanding of cosmic history, stellar evolution, the origin of galaxies, the timeline of life, inside one of those pictures. And we do not know which one is real. That is not a tension. That is not a crisis. That is the edge of the map. And beyond it, nothing. Not yet. James Webb is not done, and neither is this story. The next piece of data may be the one that breaks the framework entirely. Watch the next video now and see what else the Standard Model cannot explain.